My name is Bill Goodway. I'm presenting from Calgary, Canada. I have a BSc in Geology from University College London and an MSc from University of Calgary. I've been working for over 40 years now in geophysics and predominantly quantitative interpretation, and I'm currently scientific advisor to QI in Calgary. So as an outline, I'll start with an introduction of deterministic simultaneous inversion, what we normally do for AVO and inversion, and just touch on the limitations and challenges as motivation for what we call direct probabilistic inversion at QI. I'll compare that to deterministic inversion. And we'll go through the DPI method, which includes things like prior information, statistical rock physics models, and the likelihood in terms of a transition matrix for the prior information and subsampling. We'll finish that portion with a DPI process flow chart and look at the Bayesian inference that's used to actually run this probabilistic inversion. And in the last third of the presentation will be the new flavor, if you like, or the new extended version of DPI, which is trying to incorporate and resolve issues to do with anisotropic DPI effects on standard AVO inversion. And I'll show some examples of how this creates false positive in isotropic inversion results by not accounting for the anisotropy. And then the last part of the presentation will include a proof of concept, a synthetic test result comparing isotropic DPI and DTI DPI. So I don't see the slide here.
Okay, let me try. Does that work, Bill?
I still can't see the slide on the screen. I can see that one. Oh, there we go. Okay, so what is deterministic inversion? It's basically a process where we start with the seismic amplitude information in terms of angle gathers, and then we invert or fit those angle gathers with some approximation to the AVO equation, the Akin-Richardson-Linearized equation. We fit the amplitudes, and we produce elastic properties from that fit, that convergence of that fit. And in that one step, we actually create these elastic properties, say AI, BPDS, and rho. And instead of having a unique fit and a result and extraction of these parameters, we end up with some non-unique range of parameters. And the reason for that is because the problem is ill-posed and unconstrained. So there's a non-unique mapping in a very basic sense once we run this AVO inversion, this deterministic inversion. The next step in a very general AVO inversion scheme would be to run a rock physics model, which converts the elastic properties into rock physics properties such as mineral content, clay, saturation, and porosity. And here again, because of the overlap of the elastic properties, we see that we can actually create even more ambiguity and non-uniqueness in that step. And then the last step generally is to actually extract one lithofacies from the range of possibilities in terms of the rock physics properties, reservoir properties, and that ends up as our solution, which is obviously not necessarily the best solution, and it ignores all the other possible non-unique solutions. So what are the detailed challenges for deterministic inversion? Basically, AVO inversion of the same seismic data will produce a non-unique elastic property. So what that means is that these elastic properties will actually equally describe the input seismic data, whatever combinations. And that's non-uniqueness because it's ill-posed. The rock physics inversion to the rock property domain compounds this problem, and hence several petrophysically discrete facies can actually have the same overlapping elastic properties. And beyond that, the interbedded facies can actually have the same response as a single package. So that's like a phi-H kind of issue. And if you have noise in the input data, this makes the problem worse, more non-uniqueness, more error. And the final issue with deterministic inversion is that accounting for the lack of low frequencies in the seismic data by incorporating low frequency model may bias result in unintended consequences. The step from the elastic properties to the rock physics properties in the rock physics model is shown here in terms of a cross-plot acoustic impedance against VPBS. And you can see the elastic properties are converted now into shale, shaly sand, and then hydrocarbon sands with varying porosities. And this mapping basically is, again, ill-posed and non-unique because the data is band limited. So what that means is that the wavelet character of the seismic data results in smooth transitions between elastic parameters, so smooth vertical transitions between layers of facies that we're interested in. And the direct transition, for example, from a shale, which is low AI, high VPBS, into hydrocarbon, gas sand, which is low AI, low VPBS, will be difficult to obtain directly. So imagine that we have an overlying shale on top of gas sand, but as a consequence of the seismic wavelet, we are forced to go through these additional layers, if you like, or these additional facies, these additional rock parameters, such as the shaly sand, because the data's limited resolution. And the band limited result will then give you these layers, such as the shaly sand or brine sand, intervened between the shale, overlying shale, and the direct contact to the hydrocarbon gas sand. So how do we resolve this? Well, this DPI process at QI goes from the input gathers directly to the lithofacies and probabilities. And now instead of one solution, we have a complete model set. And in addition to that, each lithofacies solution has its probability. So it's a one-step process. And the way it works, the technology solves the AVO inverse problem. It's a Bayesian inference, and I'll show that later. It's the non-uniqueness and deterministic inversion is addressed using geological information. So we need to actually supplement the inversion with this additional information from the rock physics response. Instead of a single solution, like I said, we have a set of solutions with naturally formulated non-uniqueness of the problem by allowing for quantitative propagation of uncertainties and probabilities. So it's a natural way of actually including a range of uncertainties into the solution for a range of lithofacies. And it's flexible because it allows integration of diverse sources of information, which is not available in the standard deterministic approach. And I'll show an example of that, of including additional information beyond elastic log properties, such as anisotropy, which will be the last part of this presentation. So we can include things like anisotropy. The results from DPI, there's a sampling component, which I'll describe, which is basically how we come up with the realizations for the range of probabilities that fit the seismic data. And this creates a high fidelity resolution output. So thin beds are correctly classified. Interbedded facies can be resolved. Unlike the deterministic resolution limit or the wavelet, we can resolve interbedded facies because the deterministic method only usually gives you a mean package. The geological constraints from the prior model in DPI make this a more robust solution in the presence of noise, whereas deterministic inversion tends to degrade rapidly with noise. I'll show an example comparison of that. And it's possible to resolve below tuning thickness. And we can characterize and discriminate facies that are similar, hence we resolved that package issue with the deterministic wavelet. And we have improvements in accuracy and resolution of the inversion results. So how is this achieved? Well, we need to include the prior information, as I mentioned, and this prior information bridges the gap between geology, geophysics, and reservoir engineering, and it's available from various sources, such as just the basic geological interpretation and depositional environment, the actual physics or rock physics of the material that we're interested in, the rocks and the saturations. And a lot of information obviously will be driven from well data. So that's an important part of deterministic inversion of DPI, is that we need to have a well sampled set of data, log data. So more is better. And the prior information was needed, like I mentioned before, because the deterministic inversion or inversion in general is opposed. We have noisy data, we need to constrain the solution space, because that's part of the ill-posed unconstrained issue in the non-uniqueness. And the result is we improve the resolution. So as I'll show in more detail, we assimilate various sources of information, so data modeling, observed data, and prior information, and then using Bayes inference, shown by this equation, we come up with the lithofasces range and the probabilistic uncertainty described for each lithofasces. So in terms of what exactly is prior information, this is just a quick example. A little bit of knowledge goes a long way, so you can probably read this easily despite the spelling. So that's the type of method that the actual incorporation of the prior information constrains and aids the solution of the probabilistic inversion. So to set this up, we start with a prior framework, this initial model. It includes a complete set of expected fasces and with different minerals, saturations, and porosities. The sequence stratigraphic fluid ordering is then incorporated. So in the vertical sense, you can get this restriction and constraints of these ordering sequences in the stratigraphy, as well as the fluid buoyancy issues. You can include the depositional environment and statistics, such as geological mapping of turbidites or fans, and restrictions, say, in oil-water contacts. And an example of that is, there's a shale transition directly to a clean sand, or there's a grade through shaly sand. So that's the kind of constraint that we can bring to bear, and it's not really available in the deterministic approach. And we have to ensure that the fasces constellation, the actual sampling, if you like, of all the possibilities in this fasces list, is broad and plausible and not yet sampled. So what that means is that even if we don't have log information or any stratigraphy, we need to be able to allow, in a probabilistic sense, we need to enable to allow that option for something we have not yet drilled. The prior framework and fasces thickness distribution is shown here. So that's set up in terms of the prior framework by describing the fasces thicknesses. So basically we get these histograms and probabilities of fasces thicknesses, which is really the framework, the sort of setting, if you like, of how we will set up the prior framework and describe the transitions. And once we've got those thicknesses, we can then come up with the transition ordering. So there's just a schematic on the right-hand side here, showing how we just have a constraint of the ordering within these individual thicknesses for the fasces. Again, ensuring that we have all the fasces, the whole broad scope of the fasces, some of which may not yet have been sampled. Combining all this goes into this thing we call a transition matrix as a set of probabilistic covariance kind of cross plot in this matrix, and it's basically a mathematical sequence stratigraphy. So it's capturing the sequence stratigraphy in the ordering in terms of mathematical scheme as a Markov chain process that models the Earth, and it describes a transition between fasces. So here is on the cross plot, you see the relationship between the fasces on the diagonal and off-diagonal covariance, and the higher probability, for instance, of a dollar siltstone following a dollar sandstone in this row, than a hydrocarbon dollar siltstone following a dollar sandstone. So it just captures the probability of something following another fasces, and the transition matrix then built by counting the number of times a given fasces is followed by a different fasces. And as a result, the diagonal contains the normalized average thickness of each fasces. So that's how the ordering and the relationships and the probabilities are built into the DPI engine. The other part of the prior framework includes a statistical rock physics model covariance matrix. So what I'm showing here are a series of cross plots, elastic property space cross plots, which have for each elastic domain, we construct this statistical rock physics sub-fasces model. And so you can see that we have, for instance, AI BPBS, AI density, and BPBS density cross plots. And we get a sense from these elastic distributions of where our fasces exist in the elastic space, as well as their range of probabilities, of how much of sort of distribution of these fasces we can actually model. And beyond that, we can actually incorporate anisotropic properties such as the ones on the bottom row. So similar kind of crossplot space, AI BPBS, AI density, but now we've included delta and epsilon. And so these are Thompson parameters for the VTI situation in terms of shales. And what we will use these elastic spaces for is to actually come up with correlation lengths, and then come up with from that we can produce the PDFs for these statistical separations. So in other words, it's like saying we can analyze all these different spaces, incorporate all this different information by computing probability distributions for these various parameters, various elastic parameters. And there's no real limit here. We can include a number of possible elastic and anisotropic parameters. And again, we need to extend the distribution to ensure that broad representations of plausible possible fascies that we may not yet have drilled. The last step of the likelihood model, the prior framework, is to come up with these multiple realizations. So what this is basically doing is coming up with the actual fit, if you like, the fit of all these multicolor realizations to the actual seismic data, which I'll show in the next in the next slide. And so this is really where we come up with a range of probabilities. We create the fascies, and we create the possible fascies and understand a probabilistic link to the seismic data to fit the seismic data. And we call this the local likelihood model. And the reason that this is a local process is because in order to come up with enough realizations to ensure convergence, we have to run up to a million multicolor realizations, and it's repeated for different windows. And this step also allows us to subsample, so we can come, starting from this input seismic sample rate, we can come up with a lower subsample, a finer subsampling, which forces the resolution into the probabilistic inversion. And the limiting nature of the seismic wavelet is used here in terms of isolating this local likelihood model in terms of a window that is approximately 1 to 2 times the wavelet. That step is what allows us to create the number of realizations that were needed to ensure convergence. And so here is actually capturing all the different components that I just described into this flowchart. So the top left here is showing the stratigraphic sampling and statistical rock physics model, the covariance matrix. That's all brought to bear in terms of this transition matrix. And then based on the prior information in this model, in this likelihood model, we go through the sampling stage where we have numerous realizations, Markov chain multicolor realizations matched to the seismic within local windows, which is shown by this wavelet. So that's a localization process that allows this to have about 1 million or more realizations. And once we have all that, that gives us the probabilities of the seismic given the fascies times the probability of the fascies, and that is proportional through Bayes' theorem to the probability of the fascies given the seismic. So that's our output neighborhood posterior, local neighborhood posterior from the inputs probabilistic descriptions and measurements. And then we take in each individual window and just sum them vertically, and that gives us the output, which is the marginal posterior, which is showing a fascies probability range. This is basically a range of these colors which represent different fascies. Could be hydrocarbon sands or sands, wet sands, and shales. And so the degree of excursion for any one of these colored fascies shows the probability range, or the range of probabilities between the different fascies. So that's the general display of the output information. and you can see that we've got quite significant resolution from the input seismic. Okay, now I'll move on to the anisotropic version of DPI, which is the main content of this webinar. So before I do that, though, I just want to describe the problem. And this is actually a drilling experience, exploration drilling that went wrong, and I was for this very effect, this BTI effect. So what we had here, this is offshore West Africa, and we had a tight well sand. So you can see that this is the model from the well sand. There were a series of sands, and they're all wet, but we could model what we might expect in the deep water. And the first sand, the top sand, was the main target. And if you compare this top sand response in the model to the actual gather from the deep water location, you can see initially that we had this significant hockey stick effect, although we have quite a strong amplitude response, quite a strong brightening amplitude response, top base of that sand. And so we knew that there was some potential VTI from the residual NMO. We had to run some preconditioning and reran the conversion, the processing to include a PSTM, and this VTI effect was removed from the high order NMO. So we flattened the data, removed the VTI, and then we could actually run the inversion. As a consequence of having this log information from the shelf well, which was wet, we could then run some Grassmann substitution. And here's a land row Euro cross plot showing the input, which was wet, and the background shale as a template. So that's your background shale mud rock. And then there were a couple of other substitution points where we had, for all the range of sands, we had an oil version and then a gas and high GOR oil. And the reason we substituted these various fluids was because we obviously didn't want the brine case, and we didn't want the gas case. And so we need to ensure that our inversion was going to give us an interpretation of a potential drilling location, which was just this oil template, this oil window template. And here's the result. So we had good data out to about 45 degrees. So we ran the inversion, deterministic inversion out to 45 degrees, and motivated by the fact that using all the angles is better than restricting the angle range. And here is an example of that intershelf shelf slope sand. This is the first A sand, and you can see it lights up on the cross section, and that's actually from the white overlay there is from a polygon that's on this Landro Neuro cross plot, which is right in this zone. And the yellow points here are actually from a yellow polygon on the section that's projected onto the cross plot. So you can see that there's a clear indication from this data, which is very robust up to 45 degrees, that this top sand is actually in the oil window, which was encouraging and motivated us to come up with a location in this cross section. However, there was some concern about the brightening effects of the amplitudes, especially towards the 45-degree angle. And so we, just for due diligence, we reran the inversion, but now restricted it to 30 degrees instead of 45 degrees. And unfortunately, this top sand disappeared out of the oil window into this wet template window. So that's sort of was some sort of concern to us. Obviously, we had now two results. One was wet, one was oil, and it was just a function of the angle. And we drilled the well, and it was wet. And the reason for that, after we got the new logs and the response from the synthetic, we could model the gradients for these various solutions. And so, because the VTI effect of the overlying shale affects the VPBS ratio as you go to higher angles, it increases on the overlying shale, which implies a decrease in the sand. And so that's basically coming from the gradient, the anomalous gradient due to the overlying BTI shale. And the isotropic wet case has a gradient of -0.24. The BTI wet has a higher gradient, so -0.12. And the isotropic oil is very close to that, it's 0.11. And the actual gather was matching the BTI wet. So this is basically the problem in the conventional world of the overlying, not accounting for the overlying BTI shale. However, in the unconventional world, which is the sort of the motivation actually for what I'll show as the proof of concept for BTI DPI in the synthetic test, is that because in the tight reservoirs we're surrounded by shales, by definition we're actually in the shale source rock. So the effects of BTI in shales is prevalent, it's everywhere. And it, in a funny way, it creates a strange false positive. But in terms of the unconventional rocks, this is a false positive brittleness trend. And so I've just got a schematic here from the Horn River. These are actual measurements in the Horn River type sand. And you can see that in the Fort Simpson, which is a BTI shale, overlying the first top sand, the Musqua. These are the parameters with their measured anisotropies for epsilon delta, epsilon 0.112 and delta of 0.1. And if you use this model just as a simple half space, you can model the increase in the overlying shale as an increase in BPBS, because what's happening in the shale is to get higher angles, both BP and BS increase, and the consequence of that increase is that the BPBS ratio in that shale increases. If you model this without the anisotropy, the AVO curve is shown here in the indigo curve here. If you include the anisotropy, it increases the gradient, as we saw in the conventional West African case. So the gradient is increased, which is shown in this lime green color. And if you then go in and run an fit to that BTI curve from the shale, but in this fit is now an isotropic fit, so there's no accounting for the BTI in this case. And if you fit that with an isotropic assumption and you plot the parameters from that fit onto an LMR cross plot or lambda mu cross plot, you can see that it's actually created this shift, this brittleness shift. So that this in the unconventional world, this is a decrease in Parsons ratio, an increase in Young's modulus, and other various. This is a constant P-wave modulus line, and that shift in what it would be the actual sand without the overlying BTI shale to the case where you've got the BTI shale distortion, that direction is exactly in the brittleness direction. So that BTI response from the overlying shale, certainly in this Horn River situation, or in other unconventional settings, if the influence of the BTI manifests itself as this brittleness shift. So how do we incorporate that into the BTI aspects into this DPI formulation, this new extended DPI? What we need is to use Ruger's BTI approximation, and this is shown here. So we've got the sort of conventional deterministic AVO with the change in acoustic impedance, reflection, the change in BPBS reflectivity for a function of sines and cosines squared of the angles. And then we've got, and then this term here is the density term. It's a function of tan squared and sine squared, density reflectivity. The last two terms are the change in Thomson parameters, or delta delta and delta epsilon as a function of angle. And these are not reflectivities anymore, these are just absolute changes. So the contribution of, say, delta delta is comparable to BPBS because it's got this sine term, sine squared term, and it's in the same range if there are small BPBS changes. The delta epsilon contributes more to the far angle, so it would be more of an impact, say, on the density term, or more confusing for the density term. So we can use this equation to make the fit in the DPI to the seismic, and then we can actually need to incorporate the statistical rock physics models, and that's now extended to 5 elastic properties, so 3 isotropic and 2 Thomson parameters, delta and epsilon. and we get the delta and epsilon estimates from the well log data, and either from sonic scanner or even from VSP data, deviated VSP well, so VSP sonic information, deviation well in the well, and VSP data from the move out and the VSP data. So here is the actual data set that we were working with for this synthetic test. It's from the Monty, and you can see the fascies here. We have an overburden and an underburden. We have a gradation from the top of the Monty of double siltstone grading into an argillaceous double siltstone. And we've got these intervening layers of dollar sandstone. You can see them here, the upper and lower, well, mostly in the upper Monty. From the log data, from the synthetic test, we have AI, BPBS, rho, and then from the sonic scanner information, we had delta and epsilon. And here is the synthetic that we will use in the proof of concept test. This cross plot now shows the covariance matrix for the elastic space, and what we have here is the various cross plots. We have AI BPBS, AI rho, AI delta, AI epsilon, and then we've got a row of BPBS versus the other elastic parameters, and then we've got the lower portions as rho versus delta, rho versus epsilon. And you can see that the overburden and underburden fascies are actually separated using the Thompson's parameters. They're quite well separated, so including that Thompson parameter information into the probabilistic inversion in this cross-plot matrix, covariance matrix of the elastic space, has helped isolate and separate these fascies by the constraint, that added constraint of the anisotropy parameters, which is actually interestingly using the anisotropy parameters and uplift into this model, into the DPI, which is not possible in the deterministic case. In fact, it's the opposite. The deterministic isotropic case, it actually causes false positives. The dollar sandstone fascies is discriminated by BPBS, so you can see that from the argillaceous double siltstone. So that's actually on the standard elastic parameters. And finally, the double siltstone and argillaceous double siltstone are partially overlapped in all domains within this elastic space. And the only way to separate that kind of ambiguity or non-uniqueness is through the other parts of the prior framework in the likelihood model, which is shown here. So here we have the transition matrix for these fascies, and you can see that the overburden fascies preferentially transitions into the double siltstone fascies. There's an almost equal probability that the double siltstone fascies transitions to the double sandstone or the argillaceous double siltstone fascies. That's shown by these two probability points in the off diagonal in the transition matrix in these colors. And the double sandstone fascies preferentially transitions into double siltstone fascies. That's shown by this green off diagonal probability. And finally, the argillaceous double siltstone fascies preferentially transitions into the double siltstone fascies, shown by this blue, dark blue point. So here are the results. So I'll be comparing various pairs of tests that we ran for sensitivity, and so I'll just describe this kind of plot. So here is the input seismic. Here is the prior model. So you see sort of basic background information, if you like, the frequency component in a deterministic inversion. So there's the distributions of probability ranges, the overburden, the three fascies we have in the Monty zone, and the underburden. And then the first thing we see here is the posterior. So here is the actual range of that posterior neighborhood likelihood model with the range of probabilities from left to right or right to left, depending on the fascies and the coloring of the fascies, which is again consistent with what I've shown before. And in the middle panel, we have the most probable fascies compared to the observed. And here is an accuracy of that fit. The top right matrix here now is actually a confusion matrix, so it's showing how well we've managed to isolate the different fascies. Essentially, what we need to see is most of the colored energy on that diagonal any off-diagonal information is the error confusion in the matrix. And you see, we've actually done a good job. We've matched the dollar sandstones quite well, including the thinnest units. We've captured the gradation of the argillaceous, of the dollar siltstone into the argillaceous dollar siltstone, and the individual layers within that, the distributions of the facies within that. And we have an accuracy of about 78, 79%. And the plots on the bottom right are basically the various elastic properties, AI, BPBS, rho, delta, and epsilon, showing the means in black overlying the actual log data and standard deviation ranges. So the standard this new BTI DPI approach has actually resolved the anisotropy and the elastic properties to a high degree of accuracy in terms of this solution for the Monte zones. If we were to run an isotropic DPI on the same input synthetic model on a BTI input, the accuracy drops considerably down to just 46%, and you can see in the confusion matrix that there's very little on the diagonal. Most of it is off diagonals, and we don't really have on the most probable panel here. We don't really have a match to the observed. So there's poor performance on the isotropic DPI with a BTI input, which is probably not surprising. And it just shows the same means and distributions that overlying the, in this case, just the elastic properties, the isotropic elastic properties. Then we can compare the amount of prior information we need. So this is the same as the first slide I showed for the output of BTI DPI, and we can compare that to limited prior information. So now, if you look at the difference between these, let's see, okay, between it's hard to go back. Right. So this is the standard input, the informed prior, and then the limited prior information. So you don't see that distribution so clearly. You don't see the model now is reduced in terms of its prior information, but the actual reduction in the accuracy of the output is not seriously affected. It's still in 78% range. And now we'll compare addition of noise to this sensitivity on this BTI DPI. This is the same as I started with, 78% noise-free case. And then we can go to the noise interference. Now we've added some interference into the synthetic, and you can see that we've reduced the accuracy quite considerably with this amount of interference. This is a fairly systematic type of interference, like multiple interference. And you can see that we've got, it's blurring, we've lost the resolution. We're still matching in a sort of very broad sense, but we've certainly reduced the probability, and you can see even from the posterior that it's quite coarse, it's not resolved, and it's probably not fitting the observed log information. And you can also see that on the confusion matrix, as well as the overlays of the means on these elastic properties and the anisotropic properties. The next thing we considered was an angle restriction. So this is the original input with the 78%. So this is the BTI, DPI, and BTI input with a maximum angle. That was the angle that was used, similar to the offshore West Africa case, 45 degrees. And here we've reduced the angle to 23 degrees. And here again, you can see that we've lost a fair bit of the classification. It's not as clear cut as the higher angle range, and we're down to an accuracy of about 70%. And the reason for this is that we're losing the uplift of identifying the anisotropic effects by reducing the angles. And so that's the negative impact of having smaller angles on a problem which is basically manifested as the BTI effect in the overlying shale at the higher angle ranges, which is why you need to use the higher angle ranges. And here is an example, actually converse example. So here is the isotropic DPI on a limited angle range. And really what this is demonstrating is that the accuracy for the isotropic case increases as you reduce the angle, which makes sense, again, because the isotropic case is not affected by the anisotropy at smaller angles. And so you get an actual, it improves the fit at the smaller angle. And by comparison, if you were to have a reduced angle with noise and the VTI DPI case on the VTI input, then you'd get similar or accuracy to the isotropic case with the noise-free isotropic DPI with a similar angle restriction. So in conclusion, DPI solves the seismic AVO problem as a Bayesian inference, and it allows for different interpretation approaches such as fascist probabilities, surface probabilities, a P10, P50, P90 model for risk analysis. It allows integration of geological information during the inversion process, such as layer thickness, stratigraphic ordering. It can resolve well below tuning thickness. It has dramatic improvements in accuracy and resolution of the inversion results, and it can characterize fasces that are very similar. The anisotropic extension of that in VTI DPI offers 2 additional elastic parameters to be able to separate the fasces and for improved classification. It overcomes the isotropic approximation when you have VTI that causes incorrect BPBS estimations and false positives in the isotropic sense. VTI DPI displays a robust result regardless of the amount of information, so the test on the limited prior was quite robust. It didn't really reduce the accuracy. However, the accuracy of the VTI algorithm does decrease by reducing the maximum angle. So it's actually a case for making sure you have adequate seismic data pre-processed, seismic data preconditioned that's robust to higher angles. And the presence of noise decreases the resolution, and the magnitude of this effect is fasces dependent. Obviously, the thinnest beds start to get unresolvable with a high amount of noise. And the application of this algorithm to real seismic data is actually currently in progress with a real data set. And that's it. Thank you for your attention.